So now this should be recording. This should automatically save to your computer with the audio as soon as you end the meeting.
Okay.
If you go to the settings up here, there should be an option to pause the recording as well, or stop the recording if you have to for any reason. As long as you're unmuted and the video is on, it should record everything here.
Okay.
If you're muted for any reason, it's not going to catch that audio.
Okay. Okay.
Do you have any other questions?
No, that's you've been very helpful. Thank you.
Absolutely.
Thank you.
All right, just give us a call if you need anything else.
Okay.
Testing, can you guys hear me? Yeah, all right. Thank you so much for coming out tonight. This is a great crowd. This is our spring Moulakis lecture. We welcome this evening Dr. Glen Miller from Texas A&M University. Glen Miller is instructional professor in the Department of Philosophy at Texas A&M. He earned a bachelor's degree in chemical engineering and a doctorate in philosophy. His teaching and research help people to understand and navigate their social, technological, and ecological environments. His current research focuses on engineering ethics, cyber ethics, and the ethics of AI. His most recent book is a co-edited volume titled Thinking Through Science and Technology, Philosophy, Religion, and Politics in an Engineered World. I'm just gonna hold it up here. Oh, there we go. Just plug that. Very good book. It's been extremely helpful to me, Glenn, so thank you for organizing that project. Glenn also is very active with student engagement and enjoys advising undergrads. Let's welcome Dr. Glen Miller.
Thank you, Dr. Daidu. And also thank you to Dr. Anya Lang, who's not able to be here, for inviting me to give the Moulakis lecture this semester. I'm honored to be here. As a prelude to this talk, I would like to spend a minute reflecting on my intellectual development, which is particularly appropriate given the venue. I earned my undergraduate degree in chemical engineering from Missouri University of Science and Technology. It's an institution that awards 95% of its degrees to scientists and engineers. And I stumbled my way into something that approximates the Herbst program, due in large part to a professor of communication named Dr. Lance Haynes. He opened my eyes to the importance of the liberal arts in making sense of the world, a condition for acting intelligently in it. On this point, etymology is instructive. The liberal arts are those proper to a person who needs to exercise their freedom in society and politics. And they can be set against the mechanical arts, which are designed to help us produce the things that we need. What I did at MST was far less coherent than what is offered through the Herbst program. And I must admit a bit of envy that you have this opportunity. After I earned my engineering degree, I did 3 years of business consulting and 7 years as an entrepreneur in the technology industry. At that point, I slowed down for a minute to think through and evaluate my career, its contribution to the business community and to society, and to determine how I should spend the next decade of my life. In doing so, I realized the intellectual tools that I used for business process reorganization, chemical engineering, etc., were inadequate for this task of assessing what were really questions of ethics and politics. And so I reached out to the one professor of philosophy at Colorado School of Mines, a peer institution to my undergraduate institution, MST, Dr. Carl Mitchum. He was teaching a graduate seminar on science, technology, and society here at CU Boulder in the fall of 2008, and he allowed me to sit in on it. The seminar jump-started my efforts to think through these problems. It was in this seminar in which I was introduced to Bruno Latour's work on actor network theory which is an inspiration for much of this talk. I am honored that he is here tonight. So it is in light of this history that I aim to share some of what I wish I would have known as an undergraduate engineering student at a point in your lives where you will be able to exercise reasonable freedom in crafting your lives and careers. As Dr. Dyduk mentioned, I teach a large class of engineering ethics. And when I ask engineering students to define engineering, the first answer I get almost always is problem solving. And that's true in a sense. It captures a sense of engineering as a way of thinking about the world. When I push them to say more and point out that so many human activities not at all related to engineering, at least some of philosophy, for example, could be explained as problem solving, especially in conjunction with problem formation, would seem to fall under the definition that they've offered. They often amend their definition to include the use of mathematics, physical sciences, and engineering sciences, and often the use of quantitative methods to create innovative technologies. This definition is correct but incomplete. And if we're thinking about what responsible engineering is, what the ethics of engineering is, and frame it this way, our analysis will also be correct but incomplete. So let me offer a more sophisticated understanding, a multidimensional understanding of what engineering is to set up the rest of the talk. I'm moving here in 5 slides that I'll go somewhat quickly through at this point, but then I'll refer to them later in the talk. So here's a good working definition for us to have in mind beyond just problem solving or changing the material lot of society. We can think of the practice of engineering as the design, development, and maintenance of socio-technical systems for the production of services, systems, and artifacts, which collectively can be referred to as technology, and also including their decommissioning when they stop being useful, guided by mathematics and the physical and engineering sciences. Here you'll notice that I emphasize the fact that it's not just technology that engineers create, they create technology that's used by people. And the people are part of the system. If any of you are industrial engineers, that whole area of engineering, that whole discipline of engineering is focused on taking the human seriously. In my extended definition, I continue. Engineering practice today normally takes place as part of a technically challenging project that is part of a collective or joint venture involving a myriad of agents. The days of an engineer hanging up a shingle like a lawyer might do is gone. And all of you as engineering students probably know that. If the University of Colorado is anything like Texas A&M, you have been doing group projects since you stepped foot on campus, for better and for worse. I'm sure all of you could share nightmare stories about groups that didn't function quite right. Third point here in thinking about what engineering is the fact that the practice is explicitly defined through the creation and publication of standards, codes, and best practices. If you want to know if you have the safety factor right for something you're building, you don't just think about it, come up with an answer. You look at one of the authoritative references that have been put together by experts in the field. In addition to that explicit definition of engineering, it's also implicitly defined or determined by the customs and traditions that are passed along to new engineers as they learn how to contribute to projects. Your undergraduate engineering program, of course, is giving you all this implicit knowledge about what it means to be a good designer or a good engineer that hopefully you're picking up. Another thing that sets engineering apart from other areas of work is the fact that engineers are often asked to assess uncertainty and manage risk, to weigh various values, and to take into account the interests of a variety of stakeholders affected either directly or indirectly by their projects. This is one reason why engineering is regulated far more closely than philosophy. If I write a bad paper, I may make you confused, or in fact, have you believe something is true that actually isn't, or think that a particular argument is valid or cogent when it's not. But it's unlikely that you will suffer physical harm unless it's a really bad lecture or paper. That's not true for engineering. You deal with physical things, and engineers deal with physical things in the world that can have significant impacts on the welfare of others. And it's not always clear that those interests are aligned. In fact, we know that often interests aren't aligned. Interests in public safety may be different than the interests of the company, which may be different than the interests of the individual engineer. Last main point here, the social institutions of engineering are shaped by the roles that engineers occupy within their organizations and the socioeconomic structures in which they work. Characteristics of the educational system that produces these engineers, and in some culture, their self-organization in professional organizations. The fact that engineers have created societies, associations, boards of professional engineers to govern what they do is really amazing. I think completely, I underappreciated it when I was an undergraduate student. I didn't realize the work that engineers have done really for the last almost 200 years since civil engineering split off from military engineering. Civil engineering, in that sense, means engineering work not applied to military goals. So it would be almost all of the engineering disciplines that are taught at CU. That since 1828, in Thomas Treadgold's definition of civil engineering, there's been different organizations of engineers trying to figure out what good engineering is, try to set up social institutions to help perpetuate that over time. And we can think about different social institutions. We can think about the National Academy of Engineering in the US, the National Society of Professional Engineers, and the different societies and organizations and associations that are organized around specific disciplines. If they're anything like Texas A&M, they are the people that offer you pizza if you come to an evening talk that they have. For the purpose of this talk, it is worth noting that these societies all have codes of ethics that, to some degree, aim to instill elements of responsibility into the work of their members. And as I mentioned already, engineering is also regulated at the state level. States have engineering practices acts, which determine who is allowed to practice engineering, and also in doing so, they must define engineering in their specific discipline, and boards of professional engineers that maintain licensure standards and requirements and sanction engineers who fail to meet their expectations. Okay, let me add one last idea, now that we have this multifaceted understanding of engineering in our head. Engineering in all of the forms I've mentioned above advances over time. While it's obvious to most engineers that best practices should change as new technologies, materials, and methods emerge, they often do not make the correlation that the social institutions surrounding engineering may shift or change, and what we think of as good or responsible engineering may change as well. Here's my thesis for the talk. By starting from this expanded understanding of engineering with a focus on socio-technical systems, of how they have changed in scope and in relations and at their boundaries, we can gain insights into elements of responsible engineering today that deserve increased attention, ones that may not be captured by existing codes of ethics and engineering practices. The argument proceeds in 5 steps. First thing I'll do is to sketch out a rich concept of socio-technical systems that's enhanced by philosophers and sociologists of technology. The next 3 steps use this foundation to examine 3 aspects of engineering: 2 problems that arise with complex systems, especially those that are computerized. These are problems that will only intensify as artificial intelligence is increasingly implemented into engineering practices. Next step is to look at changes in what could be called the regulatory layer or regulatory part of a socio-technical system. And the third aspect to examine is at the boundaries of these systems, to changes in the scope of systems that are increasingly globalized, and to the social, political, and ecological environments that are often considered to be externalities when engineers are doing their analysis. In the last section of the talk, I hope to apply these insights to to help us better understand what responsible engineering means today and in the future. Okay, first step. In the introduction to the first step is a rich account of socio-technical systems. In the introduction to an edited volume derived from a National Academy of Engineering symposium on engineering as a social enterprise, aeronautical engineer Walter G. Vincenti proposed that thinking in terms of, quote, socio-technical systems, end quote, would be congenial for engineers who are used to imagining, modeling, and manipulating technical systems. Just as engineering design can be thought to work with networks of systems that can be decomposed into components. In his interpretation, engineering is one of the subsystems of human and technological activity. Vincenti describes the process as follows. As in engineering practice, this subdivision is made so that each subsystem can be analyzed in quasi-isolation. Such analysis must be carried out, however, and this is the crucial point, with attention at all times to the interactions and constraints on the subsystems and to the eventual need to reassemble the system. Such reassembly is essential if the analysis is to be valid and the socio-technical system is to work. To analyze the subsystems of the total society, industry, business, government, engineering, and so forth, they must be divided into subsystems and subcomponents. These must then be examined individually with an eye toward reassembly. Engineers are comfortable with such a systems approach. When I think of myself as an engineering student, I think this is how I would have thought this problem should be addressed. So I'm sympathetic here. But Vincenti was quick to note some of the challenges that this brings. The analysis of all of society as a socio-technical system would obviously be a tall order. And that is clearly a blatant understatement. The difficulty is compounded by the fact that society and its major subsystems are all adaptive systems. They change with time in ways that allow them to work better, function more or less at the level they currently do, or at least survive. The overall society attempts to take account of changes originating in its subsystems, and the subsystems adapt in relation to changing demands from other subsystems and from the needs of society as a whole. Engineers, unfortunately, Vincenti says, have not had much experience in analyzing even adaptive technical systems. That limited art is only now at the conceptual stage. The image of engineering as an adaptive socio-technical system of society presents a daunting model to implement. It certainly comes closer to reality, however, than the model of engineering and society as distinct and separate entities. It can at least inform and orient our thinking. That is the end of a long quote from Vincenti. Vincenti's orientation, proposed now 25 years ago, seems even truer today. Think about the digital transformations that have taken place over this time period, the extension of the internet around the world, the development of a dynamic World Wide Web, and the integration of digital technologies into nearly all aspects of work and play. Think about the supply chains that permit a world of products to be available to so many people around the world, which brings inefficiencies through the specialization of labor, but also increases the risk of interruption or failures that are no longer endemic, that is limited to a particular area, but it can be global, pandemic, as we saw in the wake of the COVID-19 disruptions. Think about how much more attention is given to environmental impacts, which have led to innovative new products, halted or altered other projects, and are now a consideration in almost any engineering project, not just in Boulder, where concerns have been elevated for some time, but elsewhere as well. One of the easiest ways to develop the idea of a socio-technical system is to start with the ubiquitous social networks that connect you to your friends, but also, for better or worse, to your parents, their friends, and your grandparents, their friends, and so on. 30 years ago, some people were known for having strong social networks, but these networks were human connections with technology used as a transitory medium. Contrast this to Mark Zuckerberg's so-called social network, which causes a similar effect, but provides a stable technological platform that serves as a hub for information exchanges through various interfaces. In between the agents and the platforms are systems and devices, including the internet, our mobile phones, computers, tablets, etc. Cognizant of the computing and information technology systems that mediate communications on the socials, it seems more accurate to call them socio-technical systems or socio-technical networks. When we express ourselves on social media, we are expecting to be part of a conversation. Web 1.0 is mostly one-directional speech, but Web 2.0 is designed to be interactive. And as digital natives are well aware, we must be attuned to our audiences. When I express myself on social media, prudence demands that I ought to anticipate responses by the present company, as it were, but also to the possibilities of decontextualization and recontextualization on the platform. A snippet of what I have said can be interposed in another conversation, perhaps outside of my knowledge, but as it is passed in different ways through social networks, ultimately affect me again, perhaps by changing my reputation. In this way, the agents on the network influence each other. A simple model of individual intention and action overlooks the implicit and explicit influences that agents have on each other. The socio-technical network that I've described at this point includes technological mediation that, in Don Idy's terminology, can amplify, extend, or otherwise transform what I do, what he calls embodiment relations, and alter how I experience or interpret the world, what he calls hermeneutic relations. The work of algorithms in social media also helps us understand the general idea of socio-technical systems. Among their many functions, algorithms determine how much attention social media posts get. In a sense, these algorithms are the prime audience for social media users, and they can thought to serve as a quasi-other in a socio-technical network, what Idy calls an alterity relation. When I make a post on social media, what I need is for the algorithm to amplify it. I actually don't care what my close circle of friends thinks about what I post. In another sense, these algorithms can be seen as manipulating the information environment in which we work, with no human intervention directly responding to the state of affairs. Idy calls this a background relation, and his favorite example is a thermostat. But for us in the digital age, we may think of a device that throttles internet traffic when certain conditions are met. Sorry, there are the four mediations from Don Idy: embodiment relations, hermeneutic relations, alterity relations, and background relations. On this understanding of a socio-technical network, one that most of us experience frequently, we can map engineering activities. They add a productive dimension to the communicative network sketched above. If I want to make a new widget, I can think about the suppliers with whom I need to collaborate, the labor that is needed to make the widget, the potential market for my widget. But a practical engineer, a phrase that sounds redundant, as it seems to me this characteristic is hardwired into engineers, will also be attuned to the technologies that play key roles in these activities. Of course, technologies often fade into the background until they misfunction, when they become present at hand. The integration of people and devices is perhaps most easily seen in the logistics network that seamlessly pass products through complex supply chains. A supply chain could be considered a socio-technical system or part of a socio-technical system, but it also could be decomposed into smaller systems or subsystems. And it is worth noting that the term supply chain assumes a fixed arrangement that is mostly one-dimensional, that understates the multiplicity of connections between nodes and the possible courses of action in the same way that the food chain is more accurately described as a food web. While products flow in one direction in supply webs, information flows back and forth, and all of the agents can change their actions in response to others. For computer scientists in the audience, there was forward prop, backward prop, and lateral propagation. Let me mention one other concept from philosophy of technology that may be useful as we think through socio-technical networks and socio-technical systems in the world. The images I have sketched above indicate a clear distinction between user and technology, and it is not clear this sharp distinction is called for. Donna Haraway has argued that we should consider ourselves cyborgs, hybrids with our technologies, that humans and their technologies cannot be clearly separated. Starting in the 1980s, she continually encouraged intellectuals to realize that a possible and perhaps compelling answer to the question of what am I is a socio-technical system. Haraway taught here for many years. My sense is that the socio-technical systems that I described above will help you have a more sophisticated understanding of engineering work that you do and the way those systems and products affect your users. Now let me put a few of these ideas to use in thinking through what responsible engineering means today. On the screen here, on the visual for the people watching a recording, you can see a simple mock-up of a socio-technical system that comes from ASCE magazine from an article in it. And it shows the interactions between participants at the bottom. This is happening at the micro level. And then within each of the realms, each of the systems, there are decisions and interdependencies between the various systems. This is one way this is depicted in the engineering literature. Okay, next part, complexity, visualization, and socio-technical networks. The first aspect of responsible engineering and socio-technical networks that I aim to investigate is the increasing integration of socio-technical systems, which become, as they become more complex, add extra elements of risk for the engineer to consider. The problem with working with complex, stable, that is non-adaptive systems, the easier problems, according to Vincenti, can be illustrated by reviewing a classic case of engineering ethics that arose in the course of the end of the development of the Bay Area Rapid Transit System, BART, in the late 1960s. A quick clarifying point here, complex means consisting of many different parts, whereas simple is something that consists just of one part. Sometimes when we think of complex, we think of complicated, and there's often some overlap between the two, but when you hear complex through this presentation, that's what I'm trying to convey. BART was designed to optimize efficiency by eliminating operators and conductors by implementing automatic train control, ATC technology. A research engineer named Holger Kortzfang, concerned about the inadequate integration of unit testing to the system level, conveyed his concerns to management starting in 1969. 12 years after the public voted for the project, 5 years after construction began, but still a couple of years before the first segments of the system were to open. Two newly hired engineers, Max Blankensee, a senior program analyst, and Robert Bruder, an electronics construction engineer, also came to hold similar concerns. Management's response to their concerns was disappointing. As far as the engineers knew, they did nothing to correct the problems, and they criticized the engineers for their behavior. They told the engineers, don't make trouble. Put in contemporary parlance and staying with the transportation theme, the engineers were told to stay in their lane. The engineers found this unsatisfactory, so the three of them provided documentation of their concerns to a member of the BART District Board of Directors. This led to a number of newspaper articles describing the concerns and a vote of confidence being called by the board. Surprisingly, at least to my sensibility, my contemporary sensibility, a large majority of the board expressed confidence in BART management. Management responded, by firing the three employees, the three engineers, without cause. The engineers appealed to the California Society of Professional Engineers, CSPE, for support, arguing that they were aiming to satisfy what is now known as the paramountcy clause in codes of ethics, to hold public health, safety, and welfare paramount, and to notify appropriate parties when public health, safety, and property are at risk. The CSPE largely affirmed the assessment of the engineers, but BART's general manager refused to meet with the CSPE president, and a meeting between the president of the CSPE and the program chief engineer had no impact. In October of 1972, 3 weeks after the trains began carrying passengers, an ATC failure caused a train to overrun a station, injuring 4 passengers and an attendant. The accident confirmed the assessments of the 3 engineers, but they suffered in the aftermath. They said afterwards they thought their careers were disrupted by about 2 years. And BART rolls on to this day. In Stephen H. Unger's assessment, the CSPE faded out of the picture toward the end of 1972, apparently as a result of pressure from members employed by the consortium of large engineering firms running the BART project. The 3 engineers finally won out of court settlements, reportedly of $75,000, not a small amount, at a time when human life was valued at $200,000, after the Institute of Electrical and Electronics Engineers, IEEE, argued that firing engineers due to a bona fide effort to protect public health, safety, and welfare was breach of contract. The general concern that arises from complex systems was expressed by Walter C. Zimmerly, who argued that humans will never be able to model sufficiently complex systems. Indeed, common methods that engineers use to determine failure modes. Fault tree analysis starts from an undesired state of affairs, a car not starting, and reasons back to what might have caused this. Maybe it's the battery, maybe it's a wiring issue, et cetera, et cetera. Event tree analysis proceeds from the initial undesirable event or failure, taking into account the performance of other systems to determine the likely consequence. While these assessments and analysis have merit, engineers aiming for responsible risk management must realize that they suffer from important limitations. It is not possible to anticipate all of the technical problems or human errors that may lead to failure in complex systems. Event tree probabilities assigned to failure modes are imprecise and rarely based on experimental testing. How often will this pump fail? Well, that's a good question. Are we going to run it and test it 100 times to figure out what the average failure is? No, we're going to take some kind of estimate based off of historical data, which may or may not align perfectly with the pump that we purchased, because we may be using it in a different way than other people have, or than the supplier used it as they were testing it. Okay, second problem, and third problem for event tree analysis, the list of initiating events on the event tree is most likely incomplete. Moreover, these tasks of trying to figure out what may go wrong or what has gone wrong, consume resources. And these resources could be used for business growth in other areas, so there's always some incentive to give them short shrift. The problems that I've described just now are exacerbated by 2 characteristics often found in technological systems, where tight coupling and complex interactions lead to unexpected or unanticipated problems. Tight coupling has to do with how quickly an event in one system affects other systems. Complex interactions refer to the effects that components or systems have on other components or systems. Sociologist Charles Perrow called accidents that result from these characteristics normal accidents. We wouldn't think of them as such. We think of them as complex accidents. He said they're normal in the sense that he thought they're inevitable. Anytime humans start working with really sophisticated systems, even if engineers and operators do their best in planning and operations to avoid them. What does this mean for responsible engineering? As computing systems automate more of the interfaces between systems and prevent the possibility of connections between systems that were not possible before, we have a problem. These connections usually reduce human error and labor costs and boost efficiencies, but at the risk of cascading problems that can result in catastrophic failures. So responsible engineering requires special attention to these problems, to designing systems that degrade rather than fail catastrophically, and include human oversight to counter the rise of unanticipated risks. This is especially true when socio-technical systems include integration with systems operated by third parties that are proprietary, where transparency is often obscured. While the use of artificial intelligence in these socio-technical systems has the promise to reduce human errors, it also can lead to more tightly coupled systems where problems can cascade quickly without the possibility of human interaction. Okay. Next step, standards, regulation, and socio-technical systems. The focus on systems and processes that is taken, recent revelations about the relationship between Boeing and the Federal Aviation Agency, the FAA, have resulted in numerous calls for examining the processes and systems used by the aerospace firm and its employees, and for accountability for its executives on the one hand, and those of the agency, including funding mechanisms and preservation of accountability on the other. These concerns first gained significant public and political attention in the wake of the two Boeing 737 MAX crashes caused by failure of the MCAS systems, 2019, just a few years ago. But Boeing has been in the news again recently with a spate of problems, including an Alaska Airlines plane that had the emergency door fly off of it mid-flight, a wheel detaching from a plane on liftoff that damaged cars in the parking lot. I think that was at LAX, Los Angeles. What, sorry? SFO, San Francisco. Thank you. And the recent death of a quality control specialist for Boeing, a long-term Boeing employee who was being deposed in a whistleblowing lawsuit against the company. Perhaps related, I received an email from Scott Kirby, CEO of United Airlines, yesterday, telling me that, quote, "Of all the things that make me proud of our team at United Airlines, I'm most proud of the culture we've built around the safety of our employees and our customers. Safety is our highest priority and is at the center of everything we do. Unfortunately, in the past few weeks, our airline has experienced a number of incidents that are reminders of the importance of safety. While they are all unrelated, I want you to know that these incidents have our attention and have sharpened our focus." The end of the email, the selection for the email. I believe that his intent was to call me before my return flight to Texas tomorrow. I'm not sure it worked. The focus on systems and processes taken by the FAA aligns with the general argument of this paper. But as it is commonly represented, it underestimates the importance of engineers. Responsible engineers are more than just cogs in a wheel. They can take actions to supplement existing systems and processes or make up for inadequacies in them. On complex technological projects, such as aircraft design and production, the roles held by engineers are a leverage intervention point in testing and certification. Yet to properly perform this role, engineers must have more than a naive understanding of regulators and regulation. At the same time, regulatory schemes should be designed to support good engineering. Regulators, regulations, and standards can strengthen or weaken the reliability of socio-technical systems. Regulators are generally thought to protect the public interest. While public interest includes concern for the welfare of the organizations an agency regulates, it must retain its potential to take adversarial positions to what the organizations it regulates hold, either independently or collectively, especially in situations in which the public interest on the whole or particular individuals or groups will be harmed or put at unnecessary risk. Regulation often strengthens the position of engineers who are involved in managing risk, as it sets standards that constrain project decisions to cut costs by decreasing quality or quality assessment. A number of trends over the last 20 years have changed the regulatory state of affairs and altered the responsibility that must be exercised by engineers. Here are the four trends. The first, delegated regulation. which has drawn attention in the Boeing case, is one such trend, also called self-regulation. This decision makes the regulated entity responsible for carrying out some steps in certification processes. For the government, this delegation promises to simplify and reduce the costs directly related to tests and indirect costs associated with recruiting and training regulators with sufficient expertise. It also allows talented individuals who would not seek a government role, whether due to interest or salary, to be included in the certification process, as well as those with specific expertise on a particular component or system. For the corporation, self-regulation promises to reduce the amount of time spent briefing regulators, increase the level of expertise specific to a component or test, and reduce one source of project delays. While a critical review of delegation decisions should be performed, it is largely expected that at least some delegation, which occurs in other countries as well, will remain. In response to a question from Congress in March 2019, the acting director of the FAA, Dan Elwell, said that his agency would require 10,000 new employees and a budget increase of $2 billion per year in order to bring back in-house all of the regulatory tasks that have been offloaded to the aviation industry. That is not happening. The second trend that affects engineering socio-technical systems is what is commonly referred to as the revolving door, the movement of individuals from industry into regulatory roles and then back into industry. This trend has the virtue of including experts who understand markets, products, and systems in regulatory efforts. But these individuals enter regulatory positions with a historical web of industry interests, relational, even if not financial, and often anticipate their reinsertion into these webs of industry at the conclusion of their regulatory appointment. While usually mentioned in connection with the financial industry or lobbyists, where you see the revolving door criticized most commonly, this movement of people provides an incentive for regulators to act contrary to the public interest when it may harm the industry or specific powerful companies, even if the decision point is not a conflict of interest situation in the strictest sense of the term, that is, having a financial interest in the decision that one makes. As you hopefully all know, if you are in a conflict of interest situation as an engineer, you are almost always required to report it. In the state of Texas, you're required to report it in writing to the parties so that they know that you have a financial interest in the decision that you may be making. An additional concern with the revolving door is that some of the individuals working in regulatory agencies are more familiar with and inclined to use methods of analysis taken from industry, which are generally developed to ensure a specific private entity's welfare, not that of the public interest. The third trend, regulatory capture, is a process by which regulated companies effectively control the agency that is supposed to regulate them, and it's related to the other two trends. The idea was originally developed by economist George Stigler, who argued that there is an economic imperative for industries that have sufficient political power to dictate regulatory actions to do so. Capture can be financial, that is, situations in which agency budgets depend on use fees or the political influence of the regulated entities. Capture can also be perspectival, also called cognitive capture, in cases in which the regulating agency adopts the concerns of the interests they are supposed to regulate. They take out over they effectively do work for their for the companies that they're supposed to keep within the public interest. Okay, the fourth regulatory trend that affects engineering is the shift from prescriptive to performative regulations. Rather than specifying exact material or process requirements, such as the thickness and spacing of studs in a wall, regulations now are starting to require projects to meet specifications determined by the project, where design adequacy is assessed using simulation and modeling software. This shift makes engineering more interesting, increasing the autonomy and space in which engineers can work, It's less just about applying a particular rule to a project, but it also makes competence and critical judgment more important for engineers as well as for those who regulate their industries. While one imagines a number of positive outcomes from this shift, it is not hard to imagine budget or profit incentives shaping one after another of an engineer's decisions until what had been over-designed misses the optimal mean and becomes under-designed. As much as engineering has embraced modeling and simulation, its practice is still shaped by imperfectly understood practices and ideas that have developed over time. The shift from prescriptive regulations to performative ones means that risk management requires thoughtful negotiation of the models that will be used to determine the performance of the product or system. And also a negotiation of how much of a safety factor should be included into a design, instead of just being able to take it from one of the standards books. Let me propose a few principles to counterbalance each trend. On delegated regulation. One possible approach to managing delegated regulation is to ensure that, as often as possible in each critical path tested, at least one delegate does not have an interest in the regulated organization's success. Ideally, each delegate's decisions, and perhaps some video recordings of critical tests, are reviewed periodically by a long-term agency member. For organizations that are doing a substantial amount of delegated regulation, states should reconsider the scope of the industry exemption, which allows non-licensed engineers to practice engineering. Licensure is an explicit statement of responsibility to the public, and continuing education requirements are an annual reminder that the engineer has an obligation to work as an engineering professional. While there are a number of reasons that industry and government employees are often exempted from licensure, not the least that there is no federal licensure for engineers, it seems reasonable to ask designees and regulators involved in technical assessments to be licensed in at least one state. On the revolving door. The issue of the revolving door is particularly hard to address. Precluding the free exercise of one's labors would also come with organizational detriment for both industry and regulators. Put differently, we could limit opportunity for individuals to participate in regulatory processes and also end up with less effective regulation. It seems that the key is to require transparency and easy access to decisions and decisions about process that new employees have made that affect the organizations from which they were previously employed. What new here means is not really clear to me, and it may be situation dependent. Perhaps we could think 4 years. That is the length of US presidential term. Disclosure could take the form of what news entities do when reporting on a financially related organization, which explicitly notes the relationship at the end or in the back matter of the document. This requirement is similar to what the National Society of Professional Engineers Codes of Ethics demands, which states that any interest that an engineer has in a topic on which they will state a public technical opinion must be disclosed at the beginning of the statement. To capture longer-term concerns, some form of disclosure could also take the form of annual reports, showing the aggregate effect of the decisions that employees have made that affect employees working as either delegates or as agency members, decisions that they have made, how they affect their previous employers. Disclosure also seems to be one way to address exit from regulatory agencies into industry. There seems to be some merit in including the creation and dissemination of major decisions that agency employees had made in the last few years as part of their exit process. This would aid transparency into the trajectories of socio-technical systems, but I must state there are many reasons to think that this would be problematic as well. Many decisions are made by groups of people. It's not always clear that these decisions would, the step of disclosure wouldn't change the judgment of the agency members, et cetera, et cetera. Okay. A second indirect way, also not without risks, is for regulating agencies to adopt decision-making processes that allow non-industry members to block important decisions, even if they are in the minority of a decision-making body, or to require consensus for decisions rather than a majority vote. Okay, so these are just different ways to try to deal with the revolving door. On performance-based regulation, licensure, which has mechanisms to ensure competence and reinforces public responsibility, seems more important when engineers are working on performance-based regulations than when the regulations stated simply what needed to be done. Licensure also addresses the problem of many hands common on many collaborative engineering projects by giving one engineer responsibility for a particular system or subsystem. Doing so is an important response to the fluidity and distributed nature of the socio-technical systems that we're talking about. The development of a testing and accreditation system for engineers could further ensure that other engineers who are part of various socio-technical systems are sufficiently competent to carry out their tasks. It also seems that a similar testing and accreditation system may also be useful for regulators who are also operating in these increasingly complex socio-technical systems. Another alternative, or perhaps supplement, to licensure and testing is the utilization of peer review, which should be employed at least periodically. Any useful regulatory action that utilizes peer review will need to be designed to reduce politically motivated peer acts and to minimize intellectual property rights concerns. My colleagues in civil engineering say that this process of peer review is increasingly common in larger public works projects and that it is often very useful. It's having another company come in at certain points in the project and look at what you've done today, look at what you plan to do in the future, and offer their expert advice on it. Apparently, that works really well. Next step, boundaries and background forces. Vincenti's explanation of the challenges of modeling socio-technical systems, which highlights the fact that systems at different levels can be analyzed, draws our attention to the limits of the systems we imagine and analyze. In this section, I will briefly touch on the limits that arise due to outsourcing, especially caused by globalization, and environmental concerns. At a general level, trends in globalization and the aim toward efficiency lead to companies controlling less of product development and production than had happened previously. This concern was raised by Dr. John Hart Smith, a Boeing Senior Technical Fellow, already in 2001. Hart Smith, an Australian who came to the US in 1968 to work for what became McDonnell Douglas, which was acquired in 2001 by Boeing, was internationally known for his expertise in aircraft structural joints and bonding. And in an internal paper that has since become famous, he argued that excessive outsourcing could cost the company its profits, intellectual property, and its long-term viability. The most important issue of all, he wrote, is whether a company can continue to operate if it relies primarily on outsourcing the majority of its work that it once did in-house. In a newspaper article on this memo in the Seattle Times in 2003, Boeing officials defended the strategy of outsourcing in order to manufacture planes more efficiently to compete with their European rival Airbus. In the same article, Joel Johnson, the vice president of international affairs with the Aerospace Industries Association, is quoted as saying, quote, "Suppliers are no longer being asked to produce widgets specified by Boeing. They are being asked to design and produce systems and subsystems." In the short term, one would expect Boeing engineers to be able to adequately manage the subsystems as they had participated in the development of their specifications and have produced parts internally for years. But this expertise is lost over time as people move on, both in Boeing and in their suppliers. What suppliers make becomes a black box, one that is analyzed based on its inputs and outputs, for which no detailed understanding is necessary. This shift runs the risk of having systems and subsystems that, when assembled, are susceptible to problems related to tight coupling and complex interactions. Perhaps more than ever, engineers are attuned to the ecological impacts of their work, which can be thought of as at the boundaries of the socio-technical systems, or it is the context in which socio-technical systems exist. The perspective that engineers have for the environment has changed more than any other area over the last 25 years, something that I would guess is more obvious to you here in Boulder, a city known for its attention to the environment for a long, long time. Life cycle analysis is one method used to take into account the use of raw materials and energy in the production of artifacts, the expected energy used and pollutants generated during their lifespan, and the impact of their decommissioning. I attempted to capture the ideas in life cycle analysis in the original definition of engineering that I offered at the beginning of the talk. In the past, such concerns have been called externalities, something beyond the scope of analysis, but that determination seems to be rapidly changing. A focus on sustainable development has also become prominent in the engineering world. It has been written into the NSPE's Code of Ethics in the most recent revision of the code. As I mentioned at the start, socio-technical systems in engineering change over time. The question of sustainable development is a challenging one, as it is a characteristic evaluated on socio-technical systems far beyond the scope of the firm or client for which an engineer works, either at a local, regional, national, or perhaps at a global level. The degree to which sustainability is a key component of good or responsible engineering depends in large part on political decisions and public attitude. Put differently, the socio-technical systems in which engineers work are shaped by broader social forces, or when thinking about sustainability, engineers need to think in terms of very expansive socio-technical networks. Okay, so what is responsible engineering today? What can we learn from socio-technical systems? The goal has been to highlight some aspects of engineering practice and of the engineering profession that deserve further investigation if one is to claim to be responsible as an engineer. This perspective serves as an antidote to the risks accompanied by detailed work that are so important for good engineering. While much of engineering work is done looking through a microscope, as it were, which provides granular insights, thinking in terms of socio-technical systems allows engineers to look up and think about the laboratory, the experiments they are running, and the goals of what they are trying to do. To practice responsible engineering, engineering professionals need to develop a multifaceted sense of identity. That is, how one thinks of oneself, that does not depend wholly on the influence of one's employer or industry. An engineer's identity is often shaped by his or her employer and industry. These organizations provide the social setting in which engineers work, and in many cases, they provide the tools that engineers need to do their work. They are also the entities that make the goods of engineering available to others, and their success usually leads to financial benefits for the engineer. Moreover, as the NSPE Code of Ethics says, engineers shall be faithful agents of their employers or clients. Yet the employer's influence needs to be balanced to assure that an engineer meets the goals of the profession. And one way to do this is to draw one's identity from relationships with other people and other entities. As mentioned above, licensure does this by drawing the engineer's attention to the role of a professional in engineering and to the professional's responsibility to the public. Licensure also gives engineers a credential that does not belong to the employer. If you're licensed by the state of Colorado. If you leave your employer, you maintain that license. Other certification that you might have done in internal training doesn't have much value if you change firms. Joining an association of engineers tends to weaken one's identity as simply an employee of a firm, and other members of the association can often offer support and provide information about different employment opportunities for those who are concerned about an employer's demands or the processes they are forcing the engineer to participate in. Toward responsible engineering, engineers also need to be taught and encouraged to incorporate the practices of reflection and imagination as essential components of their work. Reflection, which is often devalued in settings driven by profit and productivity pressures, is particularly important when working with performance-based standards or when working on ill-structured design problems, those for which no criteria for an optimal solution exists. Yet even in work that is considered normal with clearly defined objectives and processes, it still requires some reflection to ensure that the present project is solved appropriately. Beyond concerns related to engineering tasks, reflection helps an engineer to be cognizant of how the desires and demands of various stakeholders have shaped their overall project. Was there a repeated tendency to overlook inconsistencies or to allow decisions to be influenced by concerns about profit or schedule? Did the engineer experience undue pressure to deviate from good engineering practice? Has the engineer adopted a perspective or way of thinking that is incompatible with good engineering methods? Were there any process or regulations that should be changed? Are there now socio-technical systems that are too tightly coupled with no opportunity for meaningful human interaction if there is a problem that exists? Reflection provides the ground for informed imagination. Problematic habits and tendencies revealed through reflection can be corrected. Sometimes this can be done simply by firmly committing oneself to be insistent on a particular concern. Other times it can be done through discussion with one's coworkers, which could lead to a change in business practices with fellow engineers or with standards organizations, which could result in learning more about or changing processes and standards that are commonly employed in an industry, and with regulators to improve the regulatory landscape and to further understand their importance. The title of my talk tonight, What is Responsible Engineering Today?, is formulated as a question, one that has a temporal element, which captures an essential characteristic of what is required for responsible engineering. While much of engineering education and practice is focused on doing and producing, it is important to take some time, periodically, to zoom out from what one is doing, to ask whether the work is advancing the profession of engineering, your development, and societal welfare. I've gotten all but the last page here. Got all but the last page. Okay, so to ask what has changed outside of the niche areas in which one works, especially as socio-technical systems change over time, the answer to the question of what is responsible engineering today may not be satisfactory for the question of what responsible engineering is in a year or 5 years or 10 years. And the engineer needs to take agency to shape the systems that they're working in, the regulatory ones, the industry, societies, and the processes their employers use to ensure that the engineering that is done is in everyone's best interest. Thank you for your attention. Please let me know if you have any questions. We'll do a little question.
Does anybody have any questions? Do you guys have any questions? I'll run around the mic. Go ahead and make them know.
Testing? Okay. You talked about like some of the typical failure analyses that we use in engineering, but I noticed you didn't talk about like the shell model or the Swiss cheese model that we use in human factors. What do you think of the development in human factors in that field growing in order to better ensure regulation and just overall engineering design?
Could you explain the process just a little bit? I am a chemical engineer by training, but haven't practiced for a while. I have an answer to what you say, but I think it would be useful for all of us to learn a little bit more about these new techniques.
Sure, so the shell model is what we use in failure analyses. So it's called software, hardware, environmental, liveware as in the self, and then liveware as in humans collectively in general. So it's how the NTSB goes into accidents and breaks down what exactly went wrong. And then our Swiss cheese model basically is if you take a bunch of Swiss cheeses and Swiss cheese slices and line them up, sometimes you can see all the way through via the holes, and that would be what we call an active failure. But if you close one of those holes, then you don't get an active failure and we can stop it.
Thank you. I learned something on both counts. And I should say that the NTSB is one of the agencies whose work I really admire on almost everything they do. They do great work. I think these two models that may be more common with the NTSB maybe aren't quite as common in all industries, but there's certainly movements toward thinking through systems in the manner that I described in the talk here. I consider them progress. I've seen other engineering disciplines or industries adopt more and more different ways to think through failure. And I think that's all steps in the right direction. What you may want to ask yourself after thinking through this is, are there other holes still? Is there something not captured in shell or the Swiss cheese model that deserves further attention? But it sounds like progress to me. It sounds great. And all this, I don't know the history on this, but I believe most of these advances have happened in the last 20 years. Thank you.
I just have a small empirical nit question. You mentioned that the outsourcing of regulation, we're not gonna insource it again because it would require too much expense. But you know how much it's the same as growth. I mean, Airbus does have, as I understand it, a better safety record than Boeing. Is there reason to think that it's because Airbus there's more external regulation and checking on safety in Airbus than Boeing?
I don't know enough about the European regulatory scheme for aircraft to answer that with confidence. I do know that in the articles on Boeing, Hart Smith was arguing that the approach that Boeing was taking was significantly worse than the one that Airbus was taking. I would hazard a guess that the structure of Airbus is not dependent on a single entity, like the US Boeing relationship is. And I think that leads to more problems in the US, or potential problems, than what you see in Europe, where it's, I think, 3 countries that are most strongly behind Airbus and supporting Airbus. I also tend to think, and you probably could comment on this with more expertise, the European regulatory schemes seem to work more efficiently than the American ones do, or they seem to be more successful. The Europeans seem to involve academics at the right level. The regulatory agencies seem to have the power that they need, and the industries seem to be willing to accept that arrangement, where in the US, maybe it's not quite as clear where those distinctions are, and the corporations often have seems to be more power in shaping regulations.
Yeah, I think that's probably true.
I've been thinking a lot about artificial intelligence, and we read, I have my students read a couple pieces. One of them is from an EU high-level expert group on AI. And my students often say, this is really wonderful. Why aren't we doing this in the US? Yeah, that's a good question. We need to.
Hi there, thank you. Kind of following up on that, you mentioned that one point you were talking about the black box. And it sort of seems like we're at this moment where we're looking at the black boxification of engineering at an incredible scale. And, you know, we have a situation where we have all of these non-human actors, you know, who are functioning as engineers within these socio-technical systems, right? Can people even explain what they do? You know, do we know what happens in the black box? You know, when push comes to shove, you know, even people who are really intimately involved in the development of these, you know, artifacts can't explain them, right? So we're looking at trying to figure out how can they explain these non-human actors explain themselves, you know, which seems like a really difficult thing, you know, to try to figure out how to regulate or how to even, you know, articulate into the system, you know? So I'm just wondering if you could talk more about how you're thinking about AI, non-human acting, black boxification, et cetera, in how we define and engineer, let alone engineering as it is.
Yeah, thank you. Thank you for the question. I think it's a real problem or a real challenge for engineering. Especially because engineering tends to use a lot of methods and heuristics that have developed over time that they can't explicitly explain. And so you can imagine the neural network system being trained off of previous decisions where an engineer's judgment may have precluded ones that would cause failure. Artificial intelligence can't do that. That's not the way neural networks work. It seems to me that this is a challenge for engineering to state, here's the kind of competence you need to have at a granular level of what the tools you are using are doing. And I don't know if that's something like another AI that evaluates what the first AI has done, or it's something almost simpler that you do a basic analysis of the solutions that have been given to you, you know, using an approach that's either driven off of expert system AI, that is AI that's coded to do things where everyone knows what each step is, or something that's even more manual than that. Or that you model a solution that AI gives you in a way that you think is adequate for scaling up to something where things are really at risk. I think it's a great question. Even the developers of AI can't explain precisely why it does what it does. If they could do that, they would write expert system AI and it would simply do what they wanted it to do. I think it's a great question. I don't think we've even begun we've even begun to think about this as a society. AI, in my understanding right now, serves something as a very cool tool that we can use to impress people, but probably shouldn't be used for anything that really matters. If you ask me to tell you a definitive answer to something, you want to hear it from me, not from an AI that's reasonably sure or almost completely sure that something's the case. Or at least that's what I think when I go to my doctor, for example. Thank you for the question. And I think this is something for all the students to think about as you're starting to use more and more technologies that you may not understand quite so well. What do you need to know to be confident that what you're signing off on is going to do what it's supposed to? It's one thing to say, I'm reasonably sure this is going to work for ChatGPT that may be trying to write an 8th grade homework assignment. It's another thing if you're talking about what we need to do for the aircraft door. Thank you for that.
That designing and optimizing the practice of engineering should be an engineering discipline in itself, or do you think you need sort of a suite of techniques outside of engineering to confront these problems?
Explain a little more.
mean, do you like, so, you know, in engineering, you have tools like mathematical models and statistics and optimization. Do you think that these sort of, you know, regulating Boeing, for example, ideally is, you know, treated as an engineering problem, or do you think you need skills from humanities, political science, and all these other disciplines that confront that problem adequately?
Yeah, the latter, I think, the engineering approach gives you engineering solutions, which is great if the problem's an engineering problem. But if the goal is to think about how engineering affects the world and the way we should regulate engineering, or the kinds of technologies we want to have developed to give us a state where where society flourishes, you need people with expertise from outside of engineering, or at a minimum, you need students, you need engineers who have gone through something like what the Herbst program encourages you to do. That is, to think about these kinds of questions, and by doing so, that will inform your engineering, and in the process of participating in the organizations that structure what good engineering is, it will help you advance those goals in those organizations. But at the same point in time, it's great to hear other perspectives. I teach a class on the ethics of AI, and it's a nice mix of philosophers and computer scientists, and they each learn from each other. And I think that, you know, engineering's moved closer towards stakeholder analysis. Given the magnitude of the impact of engineering in the world, where almost everything I do has some kind of engineering component to it, it seems reasonable to say that the stakeholders involved in this process are all of us. And we want as many different perspectives as we can bring to the table.
Oh, is this working now? Okay. So I guess I have a question of, as I've stepped back from engineering and spoken to more people who aren't engineers, I've noticed that there's a big issue with engineers designing solutions to a problem that doesn't exist, just simply because they want to design something, or they over-engineer things because they want to sell a new product, rather than making sure that the product that they're making is specifically designed and will work for the problem at hand. Too many of my design class students want to make 5-in-1 projects. They don't want to just, you know, find a good solution that will work for that one item. They want to make it multifunctional, and in the end it ends up breaking. What do you think, how much of engineering do you think has become that, where we're in a state of society where we have solutions to so many different things that we come up with our own problems that don't exist, and thus we have waste, unnecessary waste and unethical solutions simply because we're trying to make the next big product that isn't necessary?
Yeah, great question. This isn't a new problem. Left to their own devices, engineers try to make the best mousetrap they can and build in all kinds of new features, even if the one we have already catches the mouse. So it's not new. What is new, I think, is that engineers are more attuned to that, to the question that you brought up, that they're more active in listening to other stakeholders. In some sense, corporations try to make sure engineers aren't so afflicted in over designing products that they can't sell. But engineers often now understand the importance of talking to end users to make sure the analysis is right, to involve them at different stages of the design process. So I think there's progress being made there. A great example of the problem that you state is in the work that engineers have done for people who are disabled, physically disabled. They tend to want to create super skeletons, you know, that sometimes are useful on the battlefield. But it turns out that what most people who are disabled want is an easier way to get from point A to point B, and it may be something that just has 4 wheels on it that they can roll on. So there's huge divide there. Ashley Shue has done really good work explaining the disconnect between the engineers doing work for the disabled and what the disabled community actually wants and needs. So I think there's progress, but I think you already have showing the attribute of reflection by thinking about what you're trying to do as an engineer. And if you continue that, you'll make better products, they'll be more useful to society, and you'll make more money.
I can't resist making another comment about the response of this person here, where you said, what's the problem? Is it just engineers or politics is involved? The example that you gave of outsourcing the regulatory system is a political decision to do that. And I think more engineers need to go into government. We have so few engineers in Congress, or in the Senate. I mean, it's just amazing that here's a profession that all of us are dependent upon, all those politicians, but there are not enough engineers involved in the political system. So I recommend that you become a run for Congress, and you and bring engineering into the political system.
And if you don't want to take that large step, one of the things that I do encourage my engineering students who are inclined to these kinds of problems to consider is working as an advisor for a political entity. Sometimes there are some internships that will bring people with expertise in a particular area to Washington, D.C. to work with decision makers to try to craft good policy. That's great work. And it will give you a different perspective on everything you do for the rest of your career. And you don't have to become a politician out there with campaign signs to do that, but you can have a really important role in the political process. From what I've heard, there aren't that many engineers that apply for policy internships. So if you're interested, you have a high likelihood of succeeding in that goal. Okay, thank you for your attention. Thank you for your questions.